Do you recognize this symbol D? Have you seen this for deuterium?
I have not.
Oh, okay. Well, actually, that should be coming up pretty soon in your course. So anyway, deuterium is an isotope of hydrogen. So deuterium and hydrogen basically react very similarly to each other. So that's just an isotope of hydrogen there. I guess I don't need to put in deuterium here. How about Me? This is abbreviation for methyl.
Yeah.
Okay, so it's actually a good habit to oftentimes just write Me for methyl because it gives us less clutter.
Okay.
Then over here, let's turn this into an ethyl. So I'll use ET for ethyl. That's another common abbreviation, ET for an ethyl group. Okay. All right, now that I've made up my mind, what would be a good mechanism here?
An E2 reaction.
Yeah, we have a strong bulky base. Again, strong bulky base almost has to be E2. Unless this is a methyl, this would have to be E2. Okay, now, so which hydrogen is going to be stolen?
The beta hydrogen.
Yeah, not this hydrogen over here. Not the alpha hydrogen, but the beta hydrogen. All right, now there's a new issue, though, that we haven't talked about, which is it turns out E2 only works if you have an antiperiplanar transition state. Have you heard those terms?
I have.
Okay, E2 only works with an antiperiplanar transition state. Basically, that means that the leaving group and the beta hydrogen have to be anti. Do you remember from Newman projections? You saw gauche and anti-conformations, right? Well, E2 only works if you can first have an antiperiplanar transition state. Now, are they anti yet? Well, I haven't drawn the Newman projections, but we can kind of see that they're not pointing opposite to each other over here. They're actually gauche to each other. The iodine and the hydrogen here are gauche. You can see that if you drew Newman projections. So we can't do an E2 here. Does that mean that it's impossible to do an E2? Well, no, because we know there's free rotation around single bonds. So that doesn't mean we can't do an E2. It just means that first the molecule has to rotate so that the hydrogen is anti to the iodine. And then we can do the E2. So after we rotated, so we need to rotate so the hydrogen is up here. Because can you see how this would be anti to the iodine over here? If I drew a Newman projection now, looking down this bond, if we were to draw a Newman projection, the iodine now would be pointing straight down from the front circle, and the hydrogen would be pointing straight up from the back circle. So they would be anti in the Newman projection. Now we have to ask ourselves, what position are the ethyl and the methyl groups going to be on when we make this rotation? Some students find that easy and some students find that pretty difficult. But let's see, if I'm getting this correctly here, if the hydrogen is rotating up to here, the methyl group is going to be taking the place where the hydrogen used to be. The hydrogen is moving up to here, and the methyl group is going to move to where the hydrogen used to be, and then the ethyl is going to move to where the hydrogen, to where the methyl group used to be. So if we rotate around this bond, here's where all the positions would be, over here. And it's important to be able to get that right. If you have difficulty doing that rotation, the best thing is to just do Newman projections, because it's very easy to rotate Newman projections. So if you have difficulty rotating the bond line notation to be anti, you should just rewrite this as a Newman projection. And then it's very easy to rotate a Newman projection to be anti. And actually, I have a whole video series where I spent about an hour and a half going over how to use Newman projections to do E2 and the antiperiplanar transition state, so we won't spend too much time on that here together. We'll just go over stuff that's not in that other video. Okay, and now this could do the E2. Like this. Okay. All right, so one thing that we've learned here is that E2 only works if the beta hydrogen is antiperiplanar to the leaving group. But then we also learned that we should not despair if the original picture is not antiperiplanar, because you can usually easily rotate. So it will be antiperiplanar, and then you can do the E2. Okay. But let's see an important consequence of this. This actually comes up on almost all OChem tests. This is a good topic that we're having time to talk about here. How E2 relates to chair cyclohexane. E2 has some interesting issues for chair cyclohexane that's very popular on exams. Okay, so what mechanism would we expect here? E2, because we have a strong bulky base. Here's the alpha carbon, here's a beta carbon, and here's a beta carbon. Oh, but now I'm not going to use this bulky base anymore. Now I'm going to use sodium hydroxide. But if you look at your table, we would still expect E2 here, because we have a secondary alpha carbon. If you have a secondary alpha carbon, even with a non-bulky O-, you would still expect E2. So we're still going to expect E2 here. But which beta hydrogen does this base want to attack? Because there's hydrogens on both of these. And let's not think about the antiperiplanar yet for a second. What was the other rule that we learned for determining which beta hydrogen was going to be attacked?
It's going to want to attack the top one.
And why is that? That's right.
Because of substitution.
That's right. We know that we'd like to form the more substituted alkane. Substitution stabilizes alkenes. Now, if this was very bulky, it couldn't get close enough to the more substituted, but that's why it's shifted to a non-bulky base. This is not bulky, so it's going to do the Zaitsev as an elimination. So we want to attack here. Now, the next issue is you can only steal this hydrogen if it's antiperiplanar to the chlorine. Well, looking at this picture, do they look like they're anti?
Yes.
Yeah, this is pointing straight down, and this is pointing straight up. So they are anti. If you had somebody, when you're doing Newman projections, you want to imagine somebody looking down the bond. Well, if someone was looking down this bond, the chlorine on the front carbon would be pointing straight down, and the hydrogen on the back carbon would be pointing straight up. So they would be anti. All right, so this is in perfect position to do a E2 reaction. So we can now do the E2 reaction here. And we have a normal mechanism that looks like this. We won't go ahead with the product here. Okay. Let's make some more comments about this. One thing you can see here is the only way the leaving group can ever be anti to the beta hydrogen is if they're both axial. Are you familiar with those terms, axial and equatorial, for cyclohexane? The reason that these can be anti is that they're both axial. If you think about it, there's no way that two things that are equatorial can be anti to each other, because anti means pointing in exactly opposite directions from each other. If you play around with it a little bit, you'll see that equatorial things are never pointing exactly opposite to each other. Clearly, for example, say these are clearly not anti to each other. So there's no way two things could be equatorial and be anti.
Okay.
All right, so in chair cyclohexane, things can only be anti if they're both axial. So let's think about this compound here with the same base. Well, again, we'd want to do an E2. And again, we'd like to attack the more substituted over here. Now, are these anti? This hydrogen anti to this chlorine?
No.
No, because they're equatorial. There's no way that they could be anti unless they were both axial. They have to both be axial. Does that mean that we can't do the E2 here? Well, no, we still can, because if you remember from when you were studying chair cyclohexane, can I draw this well? I drew it okay. Chair cyclohexane can flip. It can do ring flips. I don't know how much practice you had with that, but it's important now to be able to flip a chair cyclohexane. So let's see what this would look like if it's flipped. Basically, it would look like this. Think about why is this called chair cyclohexane? Here's some drawings that make it clearer why this is called chair cyclohexane. These four carbons here form the seat of the chair. Then this here is, say, the headrest, and this is the footrest. Well, how would you do a flip? Well, suppose you took the headrest and you moved it down here. Then it would become the footrest. And say you took the footrest and bent it up here, it would become the headrest.